So good evening, everyone. It's 6:15, and that's official start of our site event. Let me to welcome everyone at joint site event held by Arnika Association and International Pollutants Elimination Network. We are pleased to have you all here at the site event, which will focus on waste incineration, and we will talk about waste incineration and triple planetary crisis. Bigger part of the site event is based on the report which we published last year, and few copies are available here, or they can be downloaded on the websites, which will appear in various presentations. Waste incineration seems to be like a good solution. I'm sorry. Seems to be like a good solution, but you will see that it can cause some problems. However, I will not talk further because I will tell you more during one of the presentations. And let me to welcome here our panelists. And let me start with Jose Joel Maleon, representing Philippines. Something happened on our Zoom. We will have also online presenters. Then let me to welcome also Lee Bell from International Pollutants Elimination Network, and Gilbert Kuepouo from CREPD, Cameroon. You see the topics which they will talk about, and we will have two online presenters, Nikola Jelínek from Arnika Association and Jorge Emmanuel from Silliman University, Philippines. And my name is Jindřich Petrlík I'm from Arnika Association. I'm program director of Toxics and Waste Program. Let me to say a few words about the organizations which bring you this site event. First, about International Pollutants Network, which you, I think, mostly heard about it. It's a network uniting civil society organizations from more than 600 civil society organizations from more than 125 countries. I switched that, so sorry. And Arnika Association has a program which is focused on toxics and waste, and two of the presenters here are from this program. We host also coordination or hub for Central, Eastern, and Western Europe of IPEN, and coordinate IPEN's work focused on dioxin and POPs waste. But let me now pass the floor to first presenter, who is Nikola Jelínek, leading author of this report, which I have shown you. And she will open our site event with the theme climate change and waste incineration. So Nikola, floor is yours.
Thank you, everyone. Good evening. Can you hear me and see my presentation? I hope so.
Yes, we see it.
So I will start. My name is Nikola Jelínek. I'm an expert on toxic substances working with Arnika, which is an environmental NGO based in Czechia. And today I want to talk about the link between waste incineration and climate change, because incinerators are often presented as part of the solution, but I will try to show you why they are actually part of the problem. I'd like to start by mentioning a study I recently co-authored and about which Jindřich talked already, which is titled Waste Incineration in the Environment. It's the first comprehensive publication of its kind in a long time. It's not the first one, but there was no new record of this kind for years, and it was developed from practical experience with waste incinerator projects in Czechia and also in Europe, and based on the latest scientific findings. This study is designed to support communities affected by waste incineration and to empower active citizens and organizations with up-to-date knowledge about its environmental and climate impacts. Sorry. One of the chapters is basically part of this side event. It's the connection between incinerators and planetary ecosystem, and I will talk about it more as my also as my colleague Jindřich after me. So, have you heard of climate change? Of course, we all have, but how often do we talk about connection between waste and the climate crisis or climate change? Because waste is usually seen as a local issue, but it can have and has global climate impacts. On this picture, you can see the concept of planetary boundaries, which are basically the environmental limits we should not cross to keep Earth stable and habitable. And climate is just one of 9 boundaries. The others include chemical pollution, later called novel entities, biodiversity loss, etc. And green basically means safe, and red means we've gone too far. So in 2009, we have crossed 3 of 9 boundaries, but over time, more and more of these limits have been crossed because we gathered more scientific data and informations, and today we are far beyond safe levels in several categories. I think it's 6 of 9. And waste incineration contributes to a few of them. Because there's a connection between carbon and waste incineration, because waste contains carbon of both biogenic and fossil origin. Biogenic carbon is like food and paper, and fossil carbon it's mostly plastics made from oil. And when they are burned, they both release carbon dioxide, but only fossil carbon dioxide is counted in climate inventories. But biogenic carbon dioxide still contributes to global warming. And waste to energy plants burn both types, so those emissions are often underestimated. And you can see it on the chart on the right side. Here you can see the split. The red means the fossil carbon dioxide, and the green means the biogenic origin one. And you can see that if you count only the fossil carbon dioxide, it can be less than half of carbon dioxide emissions from the plant. Sorry, next slide. Yes. It's becoming a bigger problem because the the amount of waste which is this is for municipal waste, but the amount of municipal waste which is being incinerated is growing. And in this is data from European Union, and in 2017 it was 27% of municipal waste, and it's this amount is growing. And you can see that the um, the carbon dioxide emissions from waste incineration, which are represented by the blue line in this chart, are increasing, while the landfilling methane emissions from landfilling are decreasing, but it only means that we transfer from one of the gases that contribute to climate change to another. But waste to energy produce electricity and heat, right? Yes, they do, but they are not efficient or climate friendly. That's why is it not a climate solution? It's a high emission energy source. I will show you why. Because the average carbon intensity of the European Union in 2021 was 238 grams of carbon dioxide equivalents per 1 kWh, which means that 238 grams of carbon dioxide was released to make 1 kilowatt, the energy of 1 kWh. But if you try to find out how much carbon dioxide the waste incinerators emit. For example, in the United Kingdom, it's somewhere between 6 and 900 grams. So you can say it's basically 3 or 4 times higher, almost 4 times higher. That's why it cannot contribute to lower emissions of like the source of the energy. It's not the way how to get to zero emissions. Next slide is if incinerators to reduce production of carbon dioxide. The answer is no, because they only add new carbon dioxide emissions instead of reducing them. Because burning waste, especially plastic, doesn't replace fossil fuels. It just basically adds more emissions to the atmosphere. In this comparison shows fossil carbon dioxide emissions across different waste management options, and you can see that or waste incineration can seem like a better option than landfilling in some cases, but it still results in significant emissions of carbon dioxide, which are much higher than recycling, reuse, or waste prevention, which are far more climate-friendly solutions, not only in long-term way, but also in short term. Problem of with waste, there is like one of the biggest part of the problem is the plastic waste, because a recent study warns that by 2050, burning plastic waste will be a bigger climate problem than burning fossil fuels. So waste to energy is not a bridge to a cleaner future. It only locks us into fossil-based emissions, but from plastic, not from fuel. So that's not a way how to replace burning coal, which we are trying currently to avoid. In the future, new incinerators which are being built are going to last between 20 and 30 years. That means for 20 to 30 years, locking in emissions and delaying investments in real zero carbon alternatives. Waste incinerators are expensive, and every euro spent on incinerator is a euro which is not spent on prevention, reuse, or renewable energy. Over time, waste incinerators will have more negative and significant impact on climate change than it currently does. And the construction of those facilities supports the situation in this picture. So to conclude, waste incineration is not climate neutral. It creates emissions, delays systemic change, and reinforces fossil dependence. What we need are real solutions: reduce, reuse, recycle, and shift to clean energy. Thank you for listening, and I'm happy to answer any questions which is probably going to be after all presenters.
Exactly, Nikola. I forgot to thank you. I forgot to mention that question and answers part will be after all presentations. So if you can remember your questions and ask them in the end. And for online participants, please write your questions into the chat, and Nikola will read them in the end in that part, and we will try to answer them as well. Next presenter, in fact, is myself, and I will continue on this presentation focused on other parts of planetary crisis, which are chemical pollution and biodiversity, and also biogeochemical cycles. If you look at the waste incineration contribution to these parts, you can see that I show that we will focus on these three now. And if we start with chemical pollution, in 2022, there was published a study by a team of scientists which became with the conclusion that chemical pollution has a potential to cause severe ecosystem and human health problems at different scales, but also to alter vital Earth system processes on which human life depends. It means chemical pollution was included as one of 9 planetary boundaries in response to this understanding. And unfortunately, bad news is that we are already over that boundary. So I will try to show you how waste incineration most likely contributes to reaching this boundary, and it can be by several ways. At first, look at the flows of releases and transfer of various toxic chemicals from waste incineration. This is a kind of model. From waste incineration, there are air releases, then there are releases to water, especially when the water is used for cleaning of the air releases. Then there are transfers in wastes. This is an example of such a waste. It's a bottom ash from waste incinerator in Taiwan. Here is the example of how pollutants can be carried into the air on particulate matters, because we will talk especially about organic pollutants and heavy metals, which are bound to dust very often and particulate matters. But let me start with some new findings, because waste incineration is very often proposed as a solution for crisis with plastic waste. But here is the example that even high temperature waste incinerators used for dealing with municipal waste don't burn whole plastic. This is the residue from modern waste incinerator in Czech Republic. And there was recently published this study based on the findings from one of modern waste incinerators in China, which shows pathways of microplastics from waste incinerator. And this study found that by sampling and analysis of 31 examples from 16 modern waste incinerators operating under stable conditions, revealed that the complete destruction of plastics does not occur in these plants. The concentrations in the bottom ash ranged from 1.1 to 565 particles per kilogram. So what means in total up to more than 100,000 particles per ton of incinerated incinerated waste. So this shows that what we believed, that waste incinerators can destroy plastics, is not unfortunately truth, and waste incinerators should be counted as the source of releases of microplastics and nanoplastics. In last century, already in 1995, scientists Jay and Stiglitz looked at air emissions from waste incinerator, and they found in air emissions approximately 250 individual compounds at concentrations exceeding 50 nanograms per cubic meter, and it represented about 42% of all organic substances in emissions, while the remaining 58% consisted of unidentified aliphatic hydrocarbons. I show this because it's very often believed that air emissions and the presence of chemicals in air releases from waste incinerators is under control, because there are several scrubbers, including scrubber for catching dioxins, but we unfortunately don't measure all organic pollutants from waste incinerators, and this study has shown that to have them under control would mean to measure much broader scale of pollutants. Let me to look closer to the group of chemicals which we talked about here in Geneva already many years, and those are persistent organic pollutants. Some of them are listed under the Stockholm Convention, and we talk about the pollutants which biomagnify and which bioaccumulate and persist in the environment for a long time, and they are very toxic. They have various adverse health effects. Many of them can also influence biodiversity by, for example, influencing reproductivity of animals. This is a list of some of them which were found in releases and transfers from waste incinerators, but let me to focus on two groups. On polychlorinated dibenzodioxins and dibenzofurans, in short, dioxins, and perfluor alkylated substances and polyfluor alkylated substances, in short, PFAS. If you look at the dioxins and if we try to see whether we can be over planetary boundaries with regards to releases of this group of chemicals. We tried to calculate or estimate how much of dioxins end in waste incineration fly ashes globally. And we compared that with suggested limit values to control these chemicals in waste incineration residues. And we came to about between 7 and 15 kilograms TEQ of these chemicals per year ends in waste incineration fly ashes. And what is suggested to be out of control, it means the amount of dioxins in ash which is not considered to be POPs waste. It is equal to allowable level of dioxin in food for 133 planets Earth population, which is a huge number. Of course, not all dioxins in fly ashes reach the food chains, but even very low amount of these dioxins entering food chains is really a dangerous amount, and it means we are over planetary boundaries with dioxin from waste incineration. If we talk about the dioxins, they are dangerous in very low levels in the environment. It can be compared to one sugar cube in, for example, 1 cubic kilometer water in some lake. So just to give you idea about what levels, what concentrations we talk about, and which are already considered to be dangerous in the environment. Dioxins, they have various health effects. Some of them are carcinogenic, but mainly they are endocrine disruptors and can cause many problems, especially during ongoing exposition to these chemicals. This is example how they can enter the environment also from waste incineration as source. This is place where the fly ash from municipal waste incinerators from whole United Kingdom is stored, and this can happen there. So this is also a way which is not very often considered when we evaluate the influence of waste incineration and waste incineration residues. We tried to look in one of our studies at the fly ashes and how they are handled with regards to food chain, and we found out high levels at sites where the ashes were not handled properly, and we found high levels in free-range chicken eggs. These are summarized results in the study published in 2022. If you look at these maximum or maximal levels found in free-range chicken eggs globally, the red bars are those which are related to waste incineration. If we again come back to various flows of toxic chemicals, this is graph based on the measurements in municipal waste incinerator in Czech Republic, in Brno, and it shows in which flows, in which parts of releases or transfers from waste incinerator we can meet highest amounts of heavy metals, or also dioxins or polyaromatic hydrocarbons or polychlorinated biphenyls. You can see that many of them are in biggest part in air releases. However, heavy metals like cadmium, mercury, or then dioxins can be found more in fly ash or air pollution control residues. Unfortunately, very often fly ash or air pollution control residues are suggested to be a good material for building materials, like for filling in various constructions and so on. This way, from our point of view, could be called a kind of toxic recycling, and therefore it is important to set right limit values for content of dioxin in wastes. Let's come to PFAS. PFAS are known a very large group of chemicals, and more of these chemicals are becoming to be evaluated as POPs. Also, more and more health effects are discovered in scientific studies. Here is the list of some of their health effects. And talking about PFAS and waste incineration, it is widely believed, or at least it was widely believed, that waste incineration or burning in cement kilns can destroy PFAS. However, recent studies found that it's not full true, because PFAS were found in waste incineration residues, but also in air releases from municipal waste incinerators in, for example, in Sweden or China, or in residues which are suggested to be recycled for construction in incinerators from Czechia, Denmark, and Sweden. These are few studies which has shown or has measured PFAS in these residues. This is flow of PFAS through the waste incinerator in Sweden. So you can see that they can be found measured in air emissions, but also in waste incineration residues like bottom ash or fly ash, in the amount reaching several grams or several tens grams of PFAS per year. These are graphs showing what kind of PFAS were measured in various releases and flows. And this is the conclusion of the study, showing that especially short-chain PFCAs were primarily detected along with PFOA, PFDA, and PFBS, which were often below or close to LOQ, but the presence of short-chain PFCAs in waste-to-energy residues could be a result of either presence of precursors in waste, that degraded to the detected compound or presence of the parent compound itself in the waste. So the conclusion is that PFAS not only enter the incinerators in the waste and they are not destroyed and then released, but new PFAS can be formed during the process of waste incineration. We looked at PFAS in various waste incineration residues. We collected samples from medical waste incinerator in Philippines, municipal waste incinerators in Thailand, Czechia, and Netherlands. And these are the results which were published in Abstract for Dioxin Conference 2024. And here is a comparison with other studies. You can see that PFAS can reach levels of several tens nanograms per gram dry matter. Another way of releases of toxic chemicals from waste incineration are accidents during which uncontrolled releases are released. Arnika has put together a map of waste incineration accidents in Europe. Let's move to chemicals which are not necessarily toxic to human, but they might be harmful or dangerous for biosphere or biological or aquatic, especially aquatic organisms like zinc. Zinc is in high levels in bottom ash, and this is example from Netherlands where bottom ash from waste incinerators is largely used for construction of roads or embankments. And unfortunately, it can leak from these materials into the waters. Here is another example where fly ash, waste incineration fly ash was used for artificial coral reef in Bermuda, and contamination by heavy metals, PAHs, and dioxins was found in the sediments. This is another example. Most of waste incinerators from Sweden sent the fly ash to this island close to Oslo, island Langoya, where neighboring reserve is slowly dying. It's abandoned lime quarry, and now it's filled with fly ashes from waste incineration. Let's move to last topic, which I suggested to talk about, and it's the biogeochemical flows. We will talk, or we will focus mainly on the phosphorus cycle. It is important for keeping our soils fertile, and we gave opportunity to choose to our Minister of Environment between the options of waste incineration residues. You can guess what figure carries that, and the composting of bio-waste. And composting of bio-waste is one of the ways how to avoid a big part of waste incineration of municipal waste. And Professor Lars Stoumen Jensen from the University of Copenhagen claims that nearly 10,000 tons of phosphorus are lost in Danish incineration plants. And it corresponds exactly to the annual import of phosphates to Denmark. Here is another study showing flow of phosphorus via various waste flows in Gothenburg. and it can be connected to the fact that developed world needs to import a lot of phosphates, which are mined now in large amount in Western Sahara at this site with very long way to the port from which it goes to its destination countries. So more stuff, more information can be found in this study, which is available on these links. And we talked also about health effects of waste incineration plants evaluated by various studies, and more issues which we don't have enough room to discuss here. Thank you, and I pass now the floor to another presenter. And the next presenter is Gilbert Kuepouo from CREPD, Cameroon. I will share his presentation. And
sorry. Yeah. Hi, good afternoon or good evening, everyone. I will be short, sweet, just 5 minutes. So, what to do next?
Just wait for him to load.
What is next?
Okay, but once he gets done, I need to slow. Yes.
Yes, thank you, everyone. So I will be speaking about the POP or release from small medical waste incinerator in Africa. So it was a study that we did with Arnika, as Jindřich said. So we can see some images of small medical waste incinerator in Africa. We can see in Kenya, Gabon, nothing to do with the incinerator we saw from the Europe, but they still have the same impact in the environment, or maybe bigger impact. So in Gabon, you can see one. In Cameroon, it is even just open burning indoor, but it is called as incinerator. So next slide. So I will hail you for that one. So you still have one example here from Ghana, and then two examples from Ghana, small incinerator, medical waste incinerator. Next slide. So the problem is clear, and the statement you have in front of you is that we have been able to measure dioxin, and dioxin like PCB and other chlorinate chemical in the emission to air, as well as in bottom ashes, fly ash, and other air pollution control residue from medical waste incinerator. And this study has been published. You can see in one of the reports here by Arnika. So it is something that you can see. You can see the image at your right hand. You see the emission from one of these incinerator, but nothing is just to give you an idea. That is a so-called modern incinerator, but we are speaking about the small one we saw in the two first slides. So the statement is supported by fact, that are scientific fact. We use two matrices to sample the presence of this POP, and then I will show you in the slide. And the result of this report was presented during the dioxin conference in 2023. 2023. So this is the sample of the ash. I told you we have two matrices. We have the ash, and then you have the chicken eggs. We start with ashes, and you can see on the table here the concentration of dioxin and furan, and in terms of pictogram TQ per gram of dry weight. And then you have also the dioxin-like, and you have a total dioxin and dioxin-like PCB in the incinerator ashes that are a very high concentration. In the case of Ghana, you can see the number here. We go, it reached 2,000 pictogram TQ per gram. That is really high. And then you can compare it from the small medical incinerator in Zambia, where we have the type of open pit also. The second matrix we try to get the sample is the chicken egg, the free land chicken eggs, and you can see from this one that we still have very high concentration of dioxin and dioxin-like PCB, except for the case of the Ghana, one case of the Ghana Kumasi Hospital, where we have a total of PCB that is about 2.6 pictogram per TQ per gram fat, and you can compare to the standard, that is egg that we bought in the supermarket that are supposed to not be freelance, or they don't have a chance to maybe foreignate around the medical waste incinerator, and you can see that there is almost clean. It is green to very low level of dioxin, but you see it from the eggs that are sampled around the medical incinerator in Cameroon, Ghana, and Gabon. We see the high concentration, and these concentrations are high, are very above the limit of the maximum limit for AU in the for dioxin in eggs. That is about 2.5 pictogram per TQ per gram. So this is very concerning, and we need to take care about, as we have been discussing all this week, fighting in the contact group on the Basel Convention issue to fix the limit of low POP content. And then this is an evidence that we are facing a real challenge on the ground, and then the negotiators should think of that one. So how is that we can have dioxin can pass from medical waste incinerator to the food chain? That is the image that is trying to do it, because the freelance chicken, as you can see, can eat all these small insects in the soil around the waste incinerator, and this one also contaminated with the dioxin that are released from this small medical incinerator, and this is passed to the egg, and when we eat it, we have it in our body, and this is the scheme of the bioaccumulation that you see in the previous slide that Jindřich presents. So it is so concerning, and then the activity is already contaminated our food chain. So as with that, we conclude and we make a science-based statement that you can read directly here, that medical waste incinerator are a significant source of environmental and food chain contamination by UPOP that are unintentional POP, especially dioxin and furan. So the unregulated use of medical waste incinerator bottom ash appear to be a practice that contribute greatly to this contamination. This call for setting a more stringent low level of POT for dioxin and furan. And as they say in the discussion here, we have 3 values to choose among. We have one PPB, one PPB, and 5. 10. So the Africa region is promoting the lowest one, that is 1 ppb, that is part per billion. And then other values are very high, so we need to really choose that value to protect the human health and environment, because these ash from incinerator are used for very sensitive applications like agriculture. You see in the previous presentation, they are using it to dam on the road or and you see the emission which is there and can be released directly from where they are using to maybe expose a woman through underground water or any other thing. So that is something that we should care about, and it is a little bit that late that we have this presentation after almost the conclusion, the discussion is concluded on the low pop content, but we still have chance in plenary to maybe make a statement that will bring us to the reality. Thank you very much.
Thank you, Gilbert. And now let me to pass the floor to Dr. Jorge Emmanuel from Silliman University in Philippines, who will talk about non-combustion alternatives to medical waste incineration. Jorge, floor is yours.
Thank you, Jindřich, and to the other speakers that preceded me. Let me see. I'm not sure if you can see my screen.
We can see your screen.
Okay, excellent.
Yeah,
that's good. All right. So my let me do one more thing and change the display. There, I think that's better. My name is Jorge Emmanuel. In addition to being an adjunct professor at Silliman University, I was for quite a number of years the chief technical advisor for the United Nations Development Program, GEF projects on healthcare waste in about 8 countries or so. And I'm also one of the co-authors and co-editors of the World Health Organization's main reference manual on healthcare waste, as well as the author of a United Nations Environment Program compendium of technologies on healthcare waste. So I will talk about the non-incineration technologies that are available. But first, let me mention that the policy paper dating back a number of years ago to 2004 of the World Health Organization listed as one of its guiding principles support for Stockholm and Basel Conventions. And it specifically said that the strategy of the health sector should be to promote environmental sound management of healthcare waste, but also the effective scale-up and promotion of non-incineration technologies for the disposal of healthcare waste. So I am going to talk about the different types of non-incineration medical waste treatment technologies, and we'll show examples of this. The first few ones, the ones that are listed under steam-based technologies, are also often called wet thermal treatment methods. This is followed by the dry thermal treatment methods, dry heat systems. There's a reasonably new technology called frictional heat treatment systems for infectious waste that combine wet and dry thermal treatment. Then there are chemical disinfection systems, and one could list as part of that alkaline hydrolysis, which is a very specific and unique niche in medical waste treatment. And finally, I'll talk about specific sharps waste treatment technologies. So let's begin with the autoclaves. The autoclaves are the most common, they're the least expensive, and the most affordable for developing countries. Basically, an autoclave is a pressure vessel, and it's for the purpose of treating infectious waste using pressurized steam, which is typically at 121, at a minimum of 121 degrees C, which is equivalent to 2 bar pressure. As you can see here, the technologies can range anywhere from small ones to autoclaves that can treat close to 3 tons per hour of infectious waste. There are different ways in which we categorize autoclaves by the way they release the air, because air as an insulator makes it difficult for steam to get into the waste. And so there are different methods of trying to get rid of the air. The old way, common way, was called gravity displacement, but some of the more recent technologies use vacuum or pressure pulse to ensure that most of the air is removed, allowing the steam then to penetrate and destroy the pathogens. Pathogens meaning the microorganisms that can cause diseases. In the examples here, the one at the top is an example of a central treatment facility. This is one of my projects, and it treats the waste from most of the city of Hanoi. The one below it is another central treatment facility, autoclave, that's used in KwaZulu-Natal in South Africa. The one next to it is a US-based autoclave that is the size for a large hospital or a small group of hospitals. And then the bottom ones are examples of smaller ones. The bottom left is the one that we had developed and used during the Ebola crisis in West Africa. And that is the size of a small to medium hospital. The next one is one that's used here in the Philippines. And the smallest ones are shown at the bottom right. And these are the size of pressure cookers. This can be used in clinics, in rural settings, etc. Because actually the highest setting of a pressure cooker is the minimum temperature and pressure required for autoclave treatment of medical waste. There are today more advanced systems. These are, we call them hybrid or advanced autoclaves. And these are basically autoclaves that include a shredder or a mixing arm or internal veins, sharp internal veins, the purpose of which is to break up the bags of infectious waste and allow the steam to penetrate. And these can range anywhere from 18 kilograms per hour to more than 3 tons per hour. And because they are much more efficient, they can treat at a shorter time. For example, the regular autoclaves might require 30 minutes to 45 minutes to even an hour, depending on what the sterilization tests show. But these ones can sterilize the waste in 15 minutes or so. But they are, of course, a higher cost than the autoclaves. There are also semi-continuous, or some would just call them continuous steam treatment systems. And these are examples. And what they do is they usually have an automated feeding system with internal shredding and steam treatment. And they can range anywhere from 10 kilograms per hour to over 1 ton per hour. And these are the ones designed primarily for large-scale treatment centers. And they, too, are quite efficient. The previous examples I gave produce steam using typically an electric boiler or a gas boiler or other methods. In the case of the very small autoclaves that are like pressure cookers, those can simply be put in a stove, and you can actually use wood and charcoal to heat it up. But these systems that I'm showing now produce the steam through microwave generators or magnetrons. So the magnetron basically heats up the moisture in the waste, and often with these systems, they spray a little bit of additional water into it. and so they produce the steam. And these are also large-scale operations, but there are small batch systems, just as the ones I show at the bottom. The one at the bottom left would be for a typical large hospital or a small group of hospitals. And the next one to it is for typically a small hospital. All of those that I've discussed so far are the wet thermal treatment systems. This is an example of the dry thermal treatment system. And so they use basically hot air, but you'll notice that they operate at much higher temperatures because for us to be able to achieve the same level of disinfection or sterilization, we have to actually go to higher temperatures when it comes to hot air, because moisture is a more efficient way to destroy the pathogens, but hot air can also do it, but at higher temperatures. So this is the systems that are available now are typically for a small to medium-sized hospital, as the one shown at the top, or a very small one for doctors, clinics, and offices, as shown at the bottom. A newer system I have called frictional heat treatment systems, and they operate by using a high-speed rotor, which not only destroys the waste and breaks open the bags, but because they're operating at such high rotations per minute, they end up heating the waste, and you can get temperatures up to 150 degrees C. And the capacities for these are up to 500 kilograms per hour, which means that these are typically used for very large hospitals or treatment facilities. The next are a special category of chemical treatment, and that's alkaline hydrolysis. Alkaline hydrolysis has taken a niche role in infectious waste treatment, in medical waste treatment, because through alkaline hydrolysis, you can treat pathological waste, anatomical waste, body parts, even human cadavers, human tissues, infected animal carcasses. And in these systems, in the research that I've done, you can, for example, I have used one that's shown at the bottom, which are huge. These can take up to 4.5 tons per load. So you can put in a lot of anatomical waste or animal waste. And after about 4 to 6 hours, at the end of the process, the only thing that remains is literally calcium from the bones. The rest are broken down into basic amino acids, carbohydrates, soaps, etc. So you can have smaller examples, as the one shown at the top, from some of my projects in Latvia, for example, which handle a few kilograms per load. There are also, in general, the old chemical disinfection systems. Many of them are becoming less and less popular because of the toxic chemicals that are being used. Often they use lime slurry, peracetic acid. The old systems used to use hypochlorite, which of course can also produce POPs in the wastewater. But the new systems now use ozonation. So by the time ozonation gets to work, the only releases to the atmosphere would be basically ozone. And you can have very high treatment capacities with ozonation as well. The last thing I'll mention are the sharps waste treatment. The reason I wanted to say a few things about this is because the most dangerous category of medical waste are sharps. These are the needles, anything that's sharp, broken glass, scalpels, and so on, especially from injections. And so there are many systems dealing specifically with sharps. At the top right, for example, are the mechanical needle cutters. So what they would do is they would cut the needles from the plastic hub. There are other systems like the one next to it. We use dry heat. The one that's shown in the middle is a chemical treatment system in a central treatment facility that treats sharps waste from multiple hospitals, for example. And then there are even small ones which are used like in a small medical office or dental office where the injection is put into the container, and when it's full, a catalyst is added and the whole thing hardens, and that's an encapsulation system. So this is the range of different types of non-incineration technologies. And I just wanted to mention a few other features for all of these, except for any of the chlorinated chemical systems. But for the rest of them, no dioxins or furans are formed. There's no toxic ash. And the environmental releases in general are significantly lower compared to incineration. One of the interesting advantages of many of these systems, the steam systems, the dry heat systems, is that the materials can be recovered and recycled after sterilization. So I have had projects in Africa, in the Middle East, where we would actually take medical waste. Often we would separate the medical waste by the types of materials. For example, all the glass vials being collected from the laboratories could just be in one container. These are then put in an autoclave or in one of these other steam systems. And as long as it doesn't have a shredder, after it comes out of the autoclave, they can then be separated and recycled. We've used this for making everything from flower pots to slippers to a whole range of things. And sometimes the metal we've taken to the foundry for reuse. Even for systems that use either internal shredding or post-treatment shredding, we've also been able to separate materials using different techniques. The next thing I want to point out is the cost of these. Here I show on the graph the typical capital costs for different capacities and compared to the cost of the autoclave, which is the very bottom, the autoclave with a shredder, with a post-treatment shredder, as well as the other systems, alkaline hydrolysis, hybrid autoclaves, and so on. And you can see that they are much lower than the cost of incinerators with pollution control for the same capacity. Although I don't have a graph for it, I should also mention that the operating costs are also significantly smaller for the non-incineration technologies. So as you may have seen from the picture, there's a wide range of capacities ranging from a small rural clinic to central treatment facilities operating in the tons per hour. And now a few years ago, I did a compilation, and there are more than 100 manufacturers of these non-incineration technologies being produced in over 24 countries and being sold in all regions around the globe. So I hope this gives you a quick introduction to the alternatives to medical waste incineration. Thank you very much.
Thank you, Jorge. And now I will introduce next speaker, who is Rebel from International Pollutants Elimination Network, who will talk about non-combustion technologies for handling POPs waste.
Thank you, Jindřich. I'm not sure if this will advance the slides or whether you need to do it, but we'll try. So,
can try.
Good afternoon, everyone, and thank you for attending. I'm talking about non-combustion technology for POPs waste destruction as an alternative to incineration and its contribution to the triple planetary crisis. I'll try. Yes, it works. So what is non-combustion technology for POPs waste? There are a diverse range of technologies that do not use combustion, pyrolysis, gasification, or plasma arc to destroy POPs waste. Some are targeted at a single or limited range of POPs, and others can treat all POP waste. Most are designed specifically to destroy POPs waste. However, some can also destroy a range of hazardous wastes, including chemical weapons and industrial waste. I won't go through all of these, but I will talk a little bit about the highlighted technologies in this list. But all of this list contains non-combustion technologies, and I would also add to those mechanochemical destruction, which I'll talk about in a while, as well as treatment trains. So why should we be using non-combustion technology to destroy POPs waste? Essentially, they're able to destroy the POPs waste without generating unintentionally formed POPs like dioxins and furans in their waste streams, whether it be emissions or in their residues. Incinerators and cement kilns are being used to destroy POPs waste, but they don't overcome this problem. They require high levels of filtration to capture UPOPs using best available technique and best environmental practice. But the more of the UPOPs end up in the fly ash and in the bottom ash in the case of incinerators, or in the case of cement kilns, there's a material called CKD or cement kiln dust, which is captured in the bag houses and also contains significant levels of UPOPs. That's why they're listed in the annexes of the Stockholm Convention. This contaminated ash becomes a pollution liability for decades to come, as Jindřich showed us earlier, with deposits into landfills, onto islands and other locations, and then attempts to recycle it are problematic because it re-enters the environment and the food chain. If you're using it in cement products, it ends up going into buildings which are then demolished, and it re-enters the food chain. You can't escape the cycle when you're generating further UPOPs. Recent studies have demonstrated that incineration ash spread on land with a dioxin content above 0.05 parts per billion can contaminate the food chain to levels where the eggs produced by free-range chickens exceed the safe levels for consumption. And this is one of the reasons that IPEN has been arguing for very low POP content levels for dioxins, because the current levels are not protective. And we're seeing at the levels we currently have that the food chain is contaminated, and eggs are only one example, but they're becoming increasingly problematic. We continue to see that even state-of-the-art European incinerators are contaminating the food chain. These are the results of analysis of backyard chicken eggs in the Netherlands from the Harlingen incinerator, waste incinerator. It's a municipal waste combustion incinerator. The red dots represent eggs that exceed the European limit for dioxin. The yellow levels are slightly lower, but still excessive, and the green dots represent eggs that were sampled that came in at safe levels. And you can see the closer you get to the incinerator operation, and this is an isolated facility compared to other industrial sources in a relatively remote area, the closer you get, the higher the dioxin levels are in the chicken eggs. And if you want to look further into the issue, there's a publication on how toxic ash from incinerators poison our food chain. We are aware, for those of you who work in Stockholm, that we're required to destroy POPs waste or irreversibly transform it so that it no longer exhibits the characteristics of POPs waste, and that it shouldn't be subject to recycling and recovery operations, which is a problem that we're increasingly seeing. This is a table. It's a little bit older now. It's been updated slightly, but it's from the General Technical Guidelines on POPs waste under Basel. And what it shows is on your left vertical column, you'll see the different technologies. There's the highlighted technologies that are non-combustion technologies in black, and the rest of them are effectively combustion technologies that produce UPOPs. And the table shows you which types of POPs waste they are capable of destroying if there's information available. We're currently updating this information in the General Technical Guidelines because there's concern that temperature alone is not sufficient to justify destruction. You can't simply say that an incinerator operating at 1,000 degrees or a cement kiln operating above that is going to destroy all POPs, because there's information emerging in the scientific literature that that's not the case, and particularly the situation for PFAS at the moment. I think I've lost my presentation.
Yeah, boss.
Sorry,
Stop.
I don't know what I did.
Stop.
You mustn't press the buttons. It's coming back. I can move it along fairly quickly once you reload. Okay, and I think that's where we're up to. Moving on. I'm going to speak very quickly about a couple of these technologies that I would highlight. Gas phase chemical reduction. This was used in my hometown of Perth, Western Australia, between 1995 and 2000. It destroyed our entire POP stockpile, 2,000 tonnes of PCBs and many other POPs waste that were in the location and around Australia. It did so without generating any UPOPs emissions and without generating any ash. This, for many years, has been considered the Rolls-Royce of non-combustion technologies, and it also generates hydrogen as a byproduct, which can be used, although it wasn't at the time, for energy use in hydrogen-powered facilities. It can also this is the vessel that the barrels are placed in. At the end of the process, those barrels contained nothing and the paint was removed from them. So this hydrogen-based process destroys all organic material and it only leaves behind metals, and the metals can be recovered and they're fully decontaminated. It has very high destruction efficiencies. This is a configuration it can be established in to clean up contaminated sites and to clean contaminated soil and sludge. Multiple units can be combined for a more efficient operation. The establishment cost for the technology is around $50 million per facility for the larger facility, and about $1 million in training for the operators, because you're using hydrogen and you have to be well trained in its use. The destruction efficiencies are very, very high for this particular technology. It's been used in Japan and it's been used in the US and in Canada, I believe, and on a range of different POPs. Oh, I seem to have lost the ability to move. Do you want to advance it?
Now, move here.
Move, yeah, if you can move to the next one. Thank you. The next technology I'll talk about is BCD, base catalyzed decomposition. It works by treating the POPs waste with a mixture of hydrogen donor oil, alkali metal hydroxide, and a proprietary catalyst. It also has very high destruction efficiencies and was used to clean up the Australian Olympic site, which was contaminated with dioxins and hexachlorobenzene. It operates in this type of configuration. It's operated in many places around the world, including one of the worst dioxin contaminated sites known, which is the Spalana site in Czech Republic, which was previously a chemical manufacturing plant, but also it's operated in many other countries for this POPs waste destruction. One that is not listed currently in the general technical guidelines, but should be, is mechanochemical destruction, and it involves enclosed vessels with high-speed agitation of steel balls. And the collision of those balls ends up creating an effect which dehalogenates the chemicals inside. It's mixed with a reagent, often silicon, ground silicon, and other materials that are very low cost. And depending on how you tune that reagent material, you can achieve very high destruction efficiencies. I won't go into the chemistry of it. We don't have time, but sufficient to say that it works. It's been published in a number of peer-reviewed journal articles recently. It's been developed now for about 20 to 30 years, originating in Germany, and now being adapted for contaminated site cleanup, particularly in Vietnam at the Bien Hoa site, where the US Air Force had their Agent Orange stockpiles and contaminated heavily with dioxin. The trials there were very efficient at destruction. And that's an actual photo from the facility where they were doing this ball milling operation and treating dioxin like PCBs and dioxins. Its other advantages is that it's mobile and transportable, and they use inexpensive reagents in the material, in the processing. It means you can take the technology to the POP stockpile. So you don't have to ship your PCBs halfway across the planet to a German incinerator and pay the insurance costs and take the risk of it falling into the ocean off a container ship. You can treat the stockpile itself at the location. Industrial supercritical water is the next one I'll mention, and this has some of the same features: transportable, scalable, take it to the stockpile and operate it there. It's been used to destroy POPs waste, chemical warfare agents, and industrial hazardous waste. It's currently available as units that can be bought effectively off the shelf and is a lot easier to operate than most of the other ones. And the US Army has been using it for some time to destroy their outdated and obsolete chemical weapons. I won't go into the details too much, but it effectively is the use of supercritical water, which is heated and pressurized water at the stage just below what they call criticality. So it sort of exists in a dual phase of a liquid and a gas. And in that phase, it can oxidize chemicals and strip them down to their molecular level. And it's been very effective at doing that. And it's been part of a number of recent projects for destroying stockpiles of POPs. There you can see it in its modular form being transported in shipping containers. It's also relatively inexpensive compared to incineration, doesn't generate any UPOPs, doesn't generate any residues that need further treatment or storage or disposal. Treatment trains are when you combine these technologies with another pre-treatment technology, such as an absorption medium. So you might use some sort of absorption medium like activated carbon to soak up PFAS in contaminated groundwater. And then the second step is to destroy it in one of these POPs destruction technologies. This is an interesting one, eco spears. These are plastic spears filled with solvent, and their main purpose is to clean up sediment in areas below water. You inject these spears into the sediment, you push them in there, you leave them there for several months. They soak up the POPs because the POPs are attracted both to the plastic spears but also to the solvent inside the spears. And then you remove these spears after you've tested the sediment and it's reached the cleanup levels you want. And then you put it into a separate system for POPs destruction, including any of the ones I mentioned before. But in this case, for this company, they have a dehalogenation system, which is, I believe, an alkali metal-based system. So this is a treatment train in a different format. Another example, and the last example of a treatment train, is indirect thermal desorption combined with base catalyzed decomposition. So you heat up the, say, contaminated soil in a thermal desorption unit, and it should be indirect to prevent contamination of the exhaust gases. And then once you've distilled out the POPs in a small concentrated form, you take that and destroy it in one of the destruction technologies, with the advantage that you only have a small amount of material, much lower costs, and much lower transport of POPs waste involved. And there's a picture of that in action in Spalana in the Czech Republic, where it's in the first step been put through a thermal desorption unit, and in the second step subject to BCD destruction. There's potential for GEF funding and UNIDO co-funding and implementation of projects. There's been a number of projects that have been developed on non-combustion, and they do have a non-combustion technology program, and I think we're about to hear a little bit more about that. And there's also potential for non-combustion technology funding on POPs contaminated sites. Some of you will be aware that the new BAT-BEP guidance on POP contaminated site cleanup has just been welcomed at this COP, and that may lead to funding opportunities as people trial that guidance. I'll just move quickly through this. There's some options here for further review of the information at both Arnika and IPEN. And I'd like to thank you for your attention.
Thank you, Lee. And now we move to our last presenter, but very important one, because Jose Maleon from Environmental Management Business Philippines will present a specific example of use of non-combustion technology to destroy POPs in Philippines.
Good evening, everyone. I'll be coming from the presentation of Lee on non-burn technology. I'll be presenting one of the technology in the Philippines which we use to destroy PCBs. Now, this is one of the project funded by Jeff through the UNIDO, or the United Nations Industrial Development Organization. We had this implementation of the non-combustion technology for the treatment of PCB waste in the Philippines. So the facility is located north of Manila. It was funded by the GEF. And then, of course, before its establishment, we had several monitoring and permitting compliance. We have to secure permit, all the building permit, environmental monitoring was undertaken, baseline results from PCBs, dioxin interference in soil, water, and air. And then, of course, we were working with NGOs, the local NGOs, the Eco-Waste Coalition, during the establishment of this facility to connect with the people around the facility. And then the salient feature of the facility, which is to treat PCB oil and PCB containing equipment, it has a capacity of 720 tons per year. The process includes processing of oil up to 10,000 ppm and porous materials and metals. And then the facility has its own laboratory that uses ASTM, or kinetics method of analysis. So kinetic method is it tests only not all PCBs, not all the congeners, so that it would be faster. Major PCB types of aerochlor is being tested. So this is the inside of the facility and the operation. And then this one is the process. First, hauling of the equipment from the PCB owners. It will be hauled and brought to the facility. And then the first thing that is done is weighing, and then that's in the upper left, and then dismantling of the materials, and then loading in this decontamination chamber, and then collection of samples. After the decontamination, samples will be collected and oil and swiped from the decontaminated materials. So after that, during the process, oil sample collection, the oil will be sampled, and the recording of treatment data. So each time the oil is being sampled, it needs to be tested in the laboratory, where it will be tested if it's past the standard. The standard of the Philippines is below 2 ppm. So after the recording and data treatment, the removal of oil sludge from the settling tank. And then disposal of the decontaminated transformers. So these are metal parts which were decontaminated. This will be sold. These are all clean metal parts. So a lot of delegates have come to the facility and checked the non-burn technology, delegations from Indonesia, from India, from Azerbaijan, Myanmar, and the Regional Center for Stockholm Convention from South Africa visited the facility. So the challenges in compliance is the treatment is transport is costly for some companies that they claim they do not have the budget. But of course, with the help of the GEF, we were able to secure a project wherein with UNIDO also wherein part of the treatment would be subsidized by the project. Then some electric cooperatives threaten that they will significantly pass costs to the consumers and will increase the electric bills. So in that manner, we need to do certain interventions, which is that subsidize a portion of the treatment costs through the projects that we implement. And then lessons learned, of course, coping up with unforeseen events like the pandemic. So we did have contingency plans or mitigating plans should be in place for unplanned events like calamities, pandemic. So we need to really move quickly and put these mitigating measures in order to keep the plant operating. And then the turnover of skilled personnel. This is a specialized facility, so we had some problems with the resignation of some skilled worker or the transfer of some skilled worker. But fortunately, we were able to cope up with this by having trained personnel to train other new personnel. And then, of course, the spare parts, the order point should be established to avoid downtime of the facility. So I think that would capture the in a nutshell, that is the operation of the non-combustion POPs facility in the Philippines. Thank you.
Thank you very much. It was our last but very important speaker.